Um, okay, so let's close that one. Oops, that one. Right click, get my pointer. Okay, so cooling system, guys. Close, like I told you, heating and cooling system, guys, makes close to 25 to 30% of any electrical power system. So we have to know how to cool a building, especially the cool. You can always can heat the building with natural gas and not depend on electricity, other than moving the air. But you almost always have to use some type of an electrical cooling system. So that's what we're going to be talking guys about. Cooling system, different systems. You can the easiest, cheapest way of cooling a building is to have window air conditioning, like we said, guys. A complete single package. Throw it in the window and you cool that area. Then you get into what they call it split package system, rooftop units, cooling towers, and condensers and chillers and what's not. So there's a whole lot of systems, guys. This particular one, we're gonna focus on list the parts of a cooling system. What does a cooling system make? And you guys have heard the word evaporator, compressor, and condenser before, because we did the same something similar when we did the residential project. So we'll talk about the evaporator, the compressor, and the condenser, and what do they do for living. Describe the function of a cooling system. Like I said, evaporator, condenser, and cooling condenser and compressors. You know what I did, Adam, one time when I was working at LB Bucket? I did not understand how the heating cooling system is tied together, so I went and talked to a mechanical engineer. And I said, explain to me how this cooling tower is tied to the chiller, is tied to the air handling unit. So it's really, we're not mechanical engineers, but the more you know about the mechanical heating, cooling system, and ventilation and building, the better electrical engineer you will be, because you need to coordinate with those guys. You need to power them and most of the time, or control them, or provide some type of control for them. Then we need to do calculation, like everything else, guys. We need calculation to size the electrical component. We care less about how many cubic feet of air you need to throw out of the window or bring out of the building or bring to the building. We mainly concern, guys, about how to power these equipments. There's a wiring diagram or schematic diagrams that I go over, guys. It shows how the cooling system operates between the condenser. So that's basically what we're going to be talking about. The whole system, guys, start with something. These are what we're going to be talking about, the objective refrigeration. The whole cooling system is based on the refrigeration cycle. We'll talk about the refrigeration cycle in less than a minute here. The refrigeration cycle, guys, is based on removing heat. So removing energy in the form of heat from an object. That's what the refrigeration is. When you cool a building, Karen, you don't bring cold air. You actually remove the heat from the existing air. That's what they do. So cooling is the opposite. Cooling, guys, is the opposite of heating, obviously, but it's all related to, are you putting energy in the form of heat, or are you removing energy in the form of heat? If you remove energy in the form of heat, you're cooling. If you are bringing energy in the form of heat, you are heating that place. So it took me a while to get used to it. Cooling a building is actually removing heat, not adding cool. See what I mean? Removing the heat from it. Okay, so the heart of the cooling system, guys, is called the evaporator, and we'll talk about this one in less than a second. The evaporator, controlled by a closed loop system, and the evaporator, the refrigeration system, refrigeration cycle based on the evaporator, and it circulates so-called refrigerant, what they call it refrigerant, through the closed loop system from the evaporator into the compressor, into the condenser, and keep doing it in a cycle. This is called the refrigeration cycle. We're going to talk about it in less than a second here. Here you go. So the most important part, guys, starting with the evaporator. This is my number one evaporator. The job of the evaporator, Karen, imagine multiple coils, mechanical coils, and you have a refrigerant liquid going right through them. And you have, can you guys see that? So here's the coils going on. refrigerant liquid going right through them, and a big blower blowing the air right through these coils. And these are mechanical coils, not electrical coils. When you blow the air right through a coil that's full of a liquid, what do? That liquid is made to absorb all the heat out of it. So the refrigerant, what the refrigerant do, guys, you have a big blower here, fan, that we have to power. So here's my refrigerant, my blower inside the evaporator unit here. You blow the air right through this coil. When you blow the air, the refrigerant liquid, guys, the refrigerant liquid will gain the heat, absorb the heat, and turn from a liquid. Now it's coming right in here. There's some valve here, expansion valve to coordinate it. It goes in here, comes back as a high pressure gas. It absorbs the heat. It sucks the heat from the building, and by sucking the heat, what do? You cool the building, right? Sucking the heat, and it changes the liquid into low pressure gas. So that's the job of the evaporator. The job of the evaporator, guys, is to remove the heat from the room or that space through blowing the air right through these coils, and the liquid inside these coils will absorb the heat and change from a liquid into what they call it low pressure gas. Now the room is cold, Karen, and we picked all the heat. Now after that, now that high pressure goes into the compressor. The job of the compressor, guys, number two, the job of the compressor is two things. Number one, pull the refrigerant from the evaporator. And number two, to compress that refrigerant gas, refrigerant gas, from a low pressure gas into high pressure gas. So two functions: pull that liquid or that gas from the evaporator, as well as compress it into a high pressure. So now it goes in here, we compress it, it comes here as a high pressure gas. Still have a lot of heat in it, guys. Then it goes into, so that's the compressor, compress and pull the refrigerant. Part number three is the condenser. The condenser, guys, have a big fan right here that we have to power. A big fan that we have to power. And that fan, now there is a gas that's hot, collecting all the heat from the building. Hot gas coming from the building, collecting the heat. Now we have a big blower outside, guys, outside unit, and blow the air right through this coil. When you blow it right through this coil, what do? You pick all this heat and throw it to Mother Nature outside. Go do something with it. I don't know if you guys, if you have a central air conditioning and you put your head above the central air, do you see the heat that's coming out of, have you ever tried that one? You put your head right to the top of the unit, outside unit, and you see the heat. All this heat is coming from your house. So the condenser, guys, what it does, it condenses the high pressure gas into liquid again by removing the heat from it and throwing it to Mother Earth outside, inside the air. And so now with that condenser, we remove the heat. The outcome here is heat. Heat is out. Now we pick the heat. Remember, the heat is going here, out. Now we throw it. It changes from high pressure gas, guys, into liquid, and it circulates back again into the evaporator that continues to do the same process. That's why the refrigerant, called the refrigerant cycle. It keeps going on and on. So the last part is the expansion valve here. The expansion valve right here is just to regulate how much of this liquid is going to enter the evaporator to control the process. Any comments, guys? Any questions about these four parts? We have the evaporator, need a fan. The condenser need a fan, and the compressor, guys, here, my compressor here is also need power. So where do we interface, Adam, with this system? We need a fan for the evaporator, a fan for the condenser, and a fan and a power for the blower for the evaporator, a power for the blower for the condenser, as well as the compressor itself need to be powered. You can see where we interface as electrical, and of course also the control in between them. Any comments, guys? Any questions about these major parts of the refrigeration cycle? Major part of the refrigeration cycle. Right here, can you guys see that one right here outside the condenser? You can condense by throwing air, or you can condense by removing it through water. You know, you can remove the heat here by circulating this through water, and the water will pick up the heat and throw it outside. So this one is air. They're removing it right here through the air. Just coil is very hot, throw the air right through it, pick that heat and throw it outside. Any comments, gentlemen? Any questions? When we go to the industrial project, guys, we talk about the cooling towers and what's not and how they are interfaced. Okay, so these are the parts. Evaporator picks up the heat from the space. Condenser pulls, the compressor will pull the refrigerant that turned from liquid into a low pressure gas, pull it and compress it into high pressure gas. Condenser, guys, pick the heat out of these coils and throw it outside. And the expansion valve regulate the flow of that liquid into the evaporator. These are the major 4 parts of the refrigeration cycle. Like I said, the condenser here, guys, can be air-cooled, or you can, all these processes can be air-cooled, or it can be water-cooled, and what's not. Any comments, guys, any questions? Instead of refrigerant, Adam, in bigger buildings, they use chilled water. They chill the water, they circulate the water into an air handling unit, and that air handling unit, guys, blows air into it, get you cold air. So they use water instead of refrigerant. Okay, so that's what they did. We talked about the function, guys, of the evaporator. The function of the evaporator is to remove the heat from the interior of the building or the enclosed space. So remove it. You have big blower blowing the air right through the liquid. The liquid will pick up the heat and circulate that heat. So that's the evaporator. The condenser has two. The condenser, guys, have 2 functions. It works like a pump. It pulls that refrigerant gas, low pressure gas. It pulls it into the compressor. As well as compress it down into high pressure gas. Pressure sends it into the condenser, it pulls it from the evaporator, sends it to the condenser, and boosts the pressure, so make it high pressure gas to facilitate the operation of removing the heat from it. There's direct driven compressors, usually used in large installation. There are different types of doing the compressor, guys. For smaller installation, tend towards the hermetically sealed, and there's also the hermetically sealed compressors. They call them hermetically sealed compressors that they circulate the air right through the compressors. So these are different type of having compressors. Any comments, guys? Any questions? We have evaporator, we have compressor, we have condenser, and we have expansion valve. And each one of them has its own function. The condenser have different type, guys. Air-cooled unit. This is what I showed you. So air-cooled, they have a coil, Karen, full of hot gas, high-pressure hot gas, and you throw the air right through it and picks the hot and throw it outside. Or you can water-cooled units. You put these hot coils into a water and you pick up the heat through the water. And evaporator cooling unit, or evaporator cooling unit. So 2 different methods of doing it. Either you cool it with water or you cool it with air for the most part. What's in it for us? The condenser, guys, need a big fan or fans that we need to power. Big fan or fans need to power. What does it do? What does the condenser do for living? The first word is remove the heat from the evaporator, plus the heat of the compression. So remove the heat that got collected by the evaporator, compressed by the compressor, and throw it outside. So by removing the heat, guys, then the high pressure gas turn into liquid, and that liquid will go back again as a coolant, circulate back to the evaporator, and it keeps going. One more time. You have liquid, pick up the air, turn into a gas, low pressure gas, compress it, high pressure gas, then take it to the condenser. The condenser will pick the heat, throw it outside, and send it back as a liquid, and continue to do the process over and over. That's how refrigeration cycle is in your refrigerator, guys. If you ever go behind your refrigerator, do you see it's hot there? That's where they're throwing the heat out of that little refrigerator. Refrigeration cycle for cooling or for refrigeration, guys, the same thing. You remove the heat from an enclosure or a room and throw it outside. Okay, expansion valve, guys. Expansion valve located liquid. So what this, guys, is it's an inlet and coordinate liquid refrigerant line at the inlet to the evaporator. So it regulates the flow of the liquid, or coordinate or control the flow of the liquid into the evaporator as part of your control process for this system. Controls the rate at which the liquid flows. That's the function of that. Controls the rate at which the liquid flows into the evaporator. You need to be able to control it, to control the process. This is how they do it, guys. This is just they have a temperature sensitive valve that's tied to. So this is just a description of how this valve do. The outlet of the evaporator senses the heat of the refrigerant as it passes through the evaporator. Bulb is filled with liquid that expands and connects to a diaphragm to cause the expansion valve to meter more or less refrigerant to the coil. So this is the method. We don't need to know too much about it, but this is the method of how that valve is regulated. You know, it senses the temperature and regulates opening and closing that valve to regulate the process. Hermetic compressors. The term hermetic compressors, guys, that we're concerned about consist of a motor compressor completely sealed, cascaded in a steel casing, all in one. Refrigerant, why it's important to do that one? Then what they do, guys, they take the refrigerant gas, circulate it through the compressor over the motor winding, rotor, and bearings, and the shaft. You know what's in it for you, Derek? If you take the refrigerant over the motor shaft and winding, you cool the motor. Who cares? If you cool the motor, gentlemen, you can overwork it. Enemy number one, current of electricity is heat. If you can cool the systems, you can make them work harder. So hermetic compressors can be horses, work very hard because you're cooling them. Part of the process that they're doing is cooling, it cools itself. Okay, so by circulating the expanded gas, it will cool the motor. Who cares? It will make the motor work harder. And the NDC code book guys acknowledge this one, Derek, and assign, since these are motors, we don't go to the article 430 for them. If it's hermetic compressor, they want you to go to article 440 because it's a special type of motor. Does that make sense why we go to 440, guys, when we talk about compressor motors, condenser, and what's not? So that's how, this is just a cut through, guys, how the air going in here, and it circulates right over the windings and everything and goes as high pressure gas here. So in the process, it will cool the motor, hermetic compressor. Because it's all sealed together, it will cool the motor. Who cares? It becomes a special motor and you need to apply Article 440. Who cares? Remember yesterday we were talking about condenser. How do you size the conductor? 1.25, the overcome protection device 1.75, or you can use the nameplate on them. That's all. So typically the manufacturer, guys, will give you the nameplate on these. Any comments, guys? Any questions about hermetically compressors? Hermetic compressors sealed together, all in one. We'll talk about this one. This is a control circuit, guys, that ties all the compressors into all these systems. I'll talk about it when we, in a second here. Okay. In the project, in the commercial building that we have, not your project, the book project, we have a cooling equipment. They have two different type of cooling system. Cooling equipment for one system is for the insurance office, gentlemen, and all these locations. And this system is called single packaged cooling unit, located on the roof. It's like the window air conditioning. Very similar, single packaged window or air conditioning, rooftop unit, and it throws the air right there. Single packaged. The drugstore and the bakery, on the other hand, on this building, share a split system. Can you guys see the word split instead of single package? The split system with a compressor and condenser on a rooftop unit, that's typical, located on the roof, and the evaporators are located, the evaporator located in the basement. The evaporator located in the basement. So two systems, one of them, guys, is single and the other one is split system. You hear the mechanical contractors are talking about split system. You put the compressor and the condenser. Is a split system, Derek? Do you have an air? I don't know if you have air in central air to your house. If you have central air, the air conditioning outside, the outside unit, it has the compressor and the condenser outside. Inside, you have the evaporator inside your furnace. That's your evaporator. That's for a residential one. Commercial one, the same thing. They have the compressor and the condenser as a rooftop unit, and they have the evaporator inside with a big fan that blows and then circulate that cold air. Okay, if it's a split system, guys, or any other system, you need a duct system. So that's where our friends in mechanical engineers comes to connect the evaporator with the area to be cool. You need to take the cold air from the evaporator, channel it through exactly what they do in your house, right? You take that cold air, chilled air, and you throw fan. Well, there's a chilled refrigerant here. You throw the air right through it, guys. Pick the heat out of it. It becomes cold from the other end, and you have to circulate that cold air through your building. And to circulate it properly, what they do, guys, they use ducts. And you're familiar with ducts, registers. One right above your head, right there. So what's in it for all of us, gentlemen? We are, as electricians and engineers, we are expected to power these systems, provide power to the air conditioning units, the outside, the inside. They will also, guys, provide most of the time wiring for the control, the thermostat located in different locations. So here's a good example, guys, of where a single system versus split system here. Here's the split system. Here's your evaporator located right in here. Single system up in the roof, and you circulate them through. You circulate the whole system through ducts, multiple ducts that you can do. When it comes, guys, to so that's basically it. You have evaporator, you have condenser, you have compressor. When it comes to sizing these systems, you guys have to be aware, if it's a compressor system, you have to go to Article 440. Article 440 applies to any hermetic compressor system. If it doesn't have hermetic compressor system, it doesn't involve it, then if it's heat or cool, if it's heat, you go here. If it's motors, you go here. And if it's appliances, you go to 422. So long story short, unless it says compressor, hermetic compressor, you are to go to Article 430 if it's just a motor. It becomes a motor. They're all the same, guys. When you size a conductor 1.25, when you size the overcome protection device, for example, for here, 1.75, for here, if you're doing this one, 1.752, there's a few other options for motors that the motor will give you. Okay, there's a couple of terminologies that comes, guys, with the equipment nameplate. And these are all defined for you in the following pages, and I would like to go over them. We went through them a couple of times, guys. These 75. Okay, so the first term is called locked rotor amps. Locked rotor amps, guys, if the compressor stops, comes to a complete halt, that's the highest amount, locked rotor current. That's your locked rotor current. The current is not moving. The highest current that the motor can encounter is called locked rotor current. What's in it for you guys? We size the disconnect to be able to handle the locked rotor current. Rated load current or rated load amps. Rated load current or rated load amps, guys, you take 1.25 and you size your conductors here, or you take 1.75 and you size your overcurrent protection device. That's the full load current of the equipment. The second thing, guys, is branch circuit selection current. Branch circuit selection current is for these equipment, because they have multiple relays and multiple fans and compressors, the manufacturer tell you the branch circuit selection current that you should choose for the whole system is this amount. So long story short, what you're supposed to use is the largest of these two. Largest. So you take the largest of the rated load amps or the branch circuit selection current and you multiply it by 1.25 to size your conductors, or 1.75 to size your overcurrent protection device. So, and why do we have a branch circuit selection current? Because you have multiple equipment in one box. How are you going to size it? The manufacturers say, hey, we did our math, and here's the amp that you should use to size. They actually go further than that. You know what they go, guys? Yesterday, Derek, remember when I told you minimum circuit ampacity for the conductors and maximum overcurrent protection device? They actually give you the maximum overcurrent protection device. So they did the calculation. They did this calculation for you, and they give you the maximum overcurrent protection device is 50 amp. On the nameplate, they will tell you what type of fuse or circuit breaker and what size of fuse or circuit breaker you are to install on these equipment, on the refrigeration equipment. So they call it maximum overcome protection device. Like the chiller that we had, it says 110. You are to stick a 110. Remember that chiller condensing unit? We said 110. We stick a 110. The overcome protection device selection. Disconnect. There's also minimum, another value that's called minimum circuit ampacity. That's how you size your conductors. And this is, guys, directly coming from this value here. So minimum circuit conductors. Say minimum circuit conductor 50. You take 50, go to 310.15, size your conductors. Disconnect rating, guys. You also need to size a disconnect rating for your equipment. We basically size it based on 1.15 times the rated load amp or maximum branch circuit selection current, whichever is larger. And you size your disconnects. To summarize, guys, when you have an air conditioning, you need a disconnect, you size it 1.15. You need an overcome protection device, you size it 1.75, or you use the nameplate, whatever it says on the nameplate, maximum. You need a conductor, you size it 1.25, multiplied by rated load amp or branch circuit selection current, or you have to, if it's there, use the minimum circuit ampacity. All these terminology, gentlemen, you're required to do it. We talked about the disconnects, guys. We need, when you size your disconnect, here's your multiplier, then you use 1.25. Your disconnect also have to be horsepower rated. Your disconnect have to be horsepower rated, and for this, you have to go to this table. So when you have a disconnect, it's not enough to say 100 amp disconnect. 100 amp, 50 horsepower. So if you are to open it under load, it's not going to explode in your face. These two guys, sizing disconnects, they amp-wise as well as horsepower-wise. When we go to the commercial project, guys, I have multiple examples for you guys to be able to do. So if you have equipment, if you have multiple equipment, what they do, guys, is they take this, and you need to size the disconnect. You take the same thing, 115, you multiply it by the sum of the full load amp of all the equipment. So you have a compressor and condenser and a bunch of other things in one box. Add the full load amp for all of them, multiply them by 115, and that's how you size your disconnect. So that's, you add all the current. And also the lock rotor current. When we size the disconnect, guys, you have to size the disconnect based on the lock rotor current, as well as horsepower. As well as we have to size the amp-wise and horsepower-wise. Amp-wise, 1.115 times all the amps for all the equipment in that box. Horsepower-wise, you take the lock rotor current of all these equipments and go to the table that we were just talking about, 430.50, 251, and that will get you the horsepower rating of these equipment. One more time. Disconnect is very, very important, guys, to size the disconnect based on lock rotor current, horsepower rating. Why? Safely disconnect under full load amount of the current. If you don't size it based on horsepower, if you are to open it under load, it could explode in your face. Safely disconnect the full load current. So you need to disconnect. Set overcome protection device, guys. We requires that controllers be for controllers, which is typically installed by the manufacturer, have to be short circuit rated. You guys did the short circuit yesterday, so that tells you the short circuit withstand rating for these controllers. Overcome protection device shall not exceed the values given by the values indicated on the nameplate, the maximum overcome protection device, or 1.75. That's what we do. Overload, guys, is typically provided by the manufacturer for these equipments. Manufacturer equipment provide overload protection for various, so we typically don't get involved in provide overload. All these are part of the manufacturer. But you have to, the manufacturer have to provide an overload protection. So typically what we end up providing for most of the HVAC equipment is a fuse, a disconnect, and a feeder. A disconnect and a feeder. The last thing, guys, all these equipments are rated in tons, and we need to convert them from tons into amps. And this is just tells you don't go through that conversion. What we do, I give you guys, remember Common software? When you put the chiller in tons, it will tell you guys what the kW is. Most of the literature, manufacturer equipment literature, guys, will tell you if it's 500 tons, it will be, say, 400 kW. So we'll give you the equivalent kVA so you can size your equipment. But they size them in tons. So that's what I wanted to show you guys about these. Let me quick just flash a couple of pictures. We talked about this one, Karen, and we said the refrigeration equipment, the heart of the refrigeration is the evaporator. It blows air through a coil, picks up the heat, move the heat into the compressor, or the compressor will pull that liquid that turned into low pressure gas into compress it in the compressor into high pressure gas and push it all the way to the condenser. The condenser have blowers, blows the air right through it, pick up the heat and throw it outside, turn the high pressure gas into liquid and circulate it and regulate it through the expansion valve into the evaporator. That's your refrigeration cycle. Here's the coil that they talk about. These are not electrical coil, guys. They're mechanical coils, so the water comes in and out of these coils, or the refrigerant. Rooftop units. Here's typical rooftop units. They use them for commercial building. You see them all the time. They have the compressor and the condenser outside typically. So here's an example, guys, where the gas inlet comes in, the liquid comes out. So you have the hot gas coming in into the condenser. You blow. This is your condenser unit. You blow the air outside, take the hot air out, change the high pressure gas into liquid, and send it back into the refrigeration equipment. That's your rooftop unit. Condenser. You have your condenser, and you have your in this case, we have the condenser and the condenser right in here. Okay, so there are different ways, guys, of removing the heat. You can also use liquid to remove the heat. Look at that one. You have a hot water. You circulate. Here's the gas goes right in here. Water circulate in between, picks up the water, will picks up the heat from the refrigerant, take it all the way to a cooling tower, and remove the heat out of it through water. We'll talk about this one when we talk about commercial, industrial. Here's another method of taking, removing the heat right through that water. So air. We talked about, guys, the low pressure gas coming in, cooling the Hermetic compressor in the process. That's why we can abuse them a little bit or make them work harder. Here's a control circuit, guys, for this. Here's an air conditioning cooling cabinet here. You have the CM, which is the compressor motor. I have my compressor motor, and I have a couple of fans and what's not, and the heat cool interface and all the wiring that we need. What's in it for you guys? You need for the compressor, you need to provide a feeder right here. Like you can see, it's feeding your compressor a cabinet right in here. Compressor motor. We have a condenser fan motor also, condenser fan motor right in here fed. And EFM is evaporator fan motor, condenser fan motor, evaporator fan motor, and what's not, bunch of other things. You can see all these high pressure and low pressure and temperature, guys, controlled so the system does not explode. So that's a wiring diagram for this with the control system. We talk about split phase system when you have the evaporator in one location and the condenser in another. Single unit, guys, this is your single package unit. Everything is in one. You take you pull the air in, you remove you condense it, you remove the heat out of it, and you bring it back as a cold air, removing the heat. On the nameplate, Karen, on the nameplate of these equipment, you're going to have the voltage. You can see, guys, the voltage and the phase of frequency. Rated load amps and locked rotor current. Can you guys see that? 25 and 165. You have the condenser motor and horsepower and full load amp. Evaporator motor, the same thing. We have condenser motor, we have evaporator motor, we have compressor motor, all of them. We have the kilowatt heat strip into it. And the most important thing, Adam, is minimum branch circuit selection current, which give you how much current the whole system is going to take. The maximum fuse or circuit breaker is also given. The maximum fuse or circuit breaker is also given. Minimum branch circuit selection current, maximum fuse or circuit breaker to size your cables and feeders. Locked rotor current table, I guess, give you locked rotor current for different type of motors. For example, single phase motor 10 give you a locked rotor current at 230 of 300. That will help you size your disconnect based on locked rotor current. Again, Karen, you guys will be doing this one with me. Also, 250.1b, the same thing. If I have a 10 horsepower motor, 3-phase, burning it at 460, the locked rotor current is 363. So it will help you size a horsepower for your disconnect. 3-phase, what was that one? That was for conversion, selection of, so conversion for BC. So all these full load current, you guys are very familiar with this table, how to find the full load current for different motors, single phase and 3-phase. And that will bring us into the refrigeration cycle. To summarize, guys, you will not, guys, if you work, because we work in coordination with the mechanical engineers, if you don't understand this refrigeration cycle, you'll be always confused, always confused. We have evaporator that picks the heat from the room, and then that heat change the liquid into low pressure gas. Then it goes into the compressor. A compressor will pull it, compress it, and push it back into the condenser. Condenser will blow the heat out, change the high pressure gas into liquid, and it continues in that closed loop circle. Any comments, my friends? Any questions? Next project, I know, Brian, next project, guys, we will be doing rooftop units and chillers and whatnot. Go ahead.
I mean, what exactly does that system have to do with electrical?
Who cares? I like the word who cares. Okay, now it works. Who cares?
Yeah.
Okay, take this. We have to have a fan here that you, my friend, have to put an overcurrent protection device and a conductor. That's number one. You have to have a fan here that you, my friend, have to have a conductor and overcurrent protection device. You have a compressor here that you, my friend, have to have an overcurrent protection device and a conductor. And you see what I mean? And all the wiring in between. And all these will be all wired control. All the controlling system in between. We typically don't get into the control of it a whole lot other than connecting point to point. But you still have to provide provider. Like you guys were doing the chiller. You need a fuse, disconnect, and a feeder to feed it. That's how we interface. Now, I can tell you all this stuff and go power them and you have no idea how it works. Like I said before, the more you know about it, the better designer you will be. We're not mechanic. We care less about refrigerant as electrical engineer. But it really makes us more intelligent if we know what the system does. Don't you think so? Nobody's going to hire you to size the refrigerant for a cycle like this. But if you understand it, I'm pretty sure you'll be a better engineer.
So basically understanding the sizing of things like condenser, evaporator, all that stuff, it helps you when it comes to sizing your...
Yeah. It just helps you. Why do they have a condenser? What the heck does a condenser do for a living? What the evaporator do? What is that? You know what I mean? You hear them all in the mechanical schedule all the time. You see them, evaporator, condenser, chillers, and all this good stuff. It just helps you understand what they do for a living. You know, if it doesn't bother you, if it just say, you know, here's a motor, go size it. You know how to size a motor, great. I think it will make you a better person. You know, it's not just like lights, guys. You put a light. What does a light do for a living? Provide lights, right? We know that. What does a chiller do for a living? Chill the water. Why do we chill the water? To chill the building. How does it work? It makes you a better designer. Okay. Have I convinced you?
Yeah.
Okay. Any comments, guys? Any questions? Any comments? Any questions? That will wrap up this cooling system. Karen, you will hear Chad talk about cooling system one more time in the industrial, where we talk about rooftop units and chillers and compressors and what's not. So that's good enough for now. We'll visit this one. We visited this one 3 times. We did one in the residential, if you guys remember. Here's a commercial. We'll do one industrial. After that, Derek, you're on your own. So, okay. I'm going to give you guys 10 minutes, and then let's do SKM coordination for 20 minutes. Thank you.